Hello everyone, welcome back to my YouTube channel. I am Vaishnavi from Sri Venkateshwara College of Engineering, Department of CSE AI. Today in this video, I will be discussing about Bayesian networks and related probabilistic methods. Let us begin with the introduction to Bayesian networks. Bayesian networks are graphical models that represent probabilistic relationship among the variables. They use directed acyclic graphs DAGs to depict the dependencies. Each node in the graph represents a variable, while edges imply conditional dependencies. Components of Bayesian networks. The main components of Bayesian networks are nodes, edges, and probability distributions. Nodes represent the random variables, which can be discrete or continuous. Edges indicates the conditional dependencies, while probabilistic distributions quantify those relationships. How Bayesian networks work. Bayesian networks utilizes Bayes' theorem to update the probability estimates of hypotheses as a new evidence is available. They allow for efficient interface even in a complex networks with many variables. This makes them useful for various applications including diagnosis and decision support. Conditional independence. Conditional independence is a key concept in a concept of Bayesian networks that simplifies the computations. If two nodes are conditionally independent, given a third node, the knowledge of one does not affect the another. This property reduces the complexity of joint probability distribution. Learning Bayesian networks. Learning Bayesian networks involves estimating the structure and parameters from the data. There are two main approaches, structural learning and parameter learning. Structural learning identifies the network topology, while parameter learning focuses on estimating the probabilities associated with the edges. Inference in Bayesian networks. Inference refers to the process of computing the probabilities of certain variables given evidence. Common methods for inference include exact inference, approximate inference, and sampling methods. Each method has its advantages depending on the complexities of the network and the available data. Applications of Bayesian networks. Bayesian networks are widely used in medical diagnosis to model the relationship between diseases and symptoms. They are also applied in risk assessments, decision makings, and machine learning. Their flexibility allows them to be tailored to a variety of domains, including finance and robotics. Comparison with other models. Bayesian networks differ from traditional probabilistic models by incorporating the directed relationship. Unlike Markov networks, Bayesian networks allow more efficient representation of conditional dependencies. This makes them more suitable for a certain types of inferential problems where directional is important. Markov's networks overview. Markov's networks, also known as Markov's random fields, are another type of graphical model. They represent dependencies using undirected graphs, focusing on the joint distribution of a set of variables. While they are powerful, they do not facilitate some type of conditional dependencies reasoning as Bayesian networks. Extensions of Bayesian networks. Extensions of Bayesian networks include dynamic Bayesian networks, which include time series data. They enable the representation of temporary relationships are useful for modeling processes that evolve over time. This makes them applicable in fields like robotics and economics. Bayesian belief networks. Bayesian belief networks are a type of Bayesian networks, especially designed for a belief updating. They allow for the incorporation of expert knowledge and can handle uncertainty effectively. This makes them suitable for applications in AI and decision making systems. Probabilistic graphical models. Probabilistic graphical models encompasses the both Bayesian networks and Markov networks. They provide unified framework to represent and reason about the uncertainty. This broad category allows for the integration and various probabilistic methods and inference techniques. Parameter learning techniques. Parameter learning is a Bayesian networks and can be done using maximum likelihood estimations MLE or a Bayesian estimations. MLE maximum likelihood estimations focuses on finding the parameters values that maximize the likelihood of observed data. Bayesian estimations incorporates prior date knowledge, providing a more robust framework in the presence of limited data. Structural learning techniques. Structural learning can follow the constraint based, score based, and hybrid approach. Constraint based approaches uses a statistical tests to identify independencies in a relationship among the variables. Score based methods evaluate different structures based on how well they fit the data, using a metrics like BIC or AIC. Challenges in Bayesian networks. One major challenge in Bayesian networks is dealing with incomplete data, which can affect the inference accuracy. Scalability is another concern, as a large networks can lead to the computational difficulties. Ensuring model interpretability while maintaining complexity is also a significant challenge. Software tools for Bayesian networks. Several software tools are available for constructing and analyzing the Bayesian tools, such as Netica and Genia. These tools provide a user-friendly interfaces for more building, inferences, and visualizations. They are widely used in both academic research and industry applications. Bayesian networks in AI. In artificial intelligence, Bayesian networks play a critical role in reasoning under uncertainty. They facilitate decision-making process by providing a structured way to incorporate the prior knowledge and new evidence. This makes them valuable in applications such as natural language processing and computer vision. Future directions. The future of Bayesian networks may involve integrating them with the deep learning techniques. Research is ongoing to enhance the scalability and efficiency in large networks. Advances in computational power and algorithms will likely expand their applicability in complex domains. Conclusion. Bayesian networks are powerful tools for modeling uncertainty and probabilistic reasonings. Their versatility allows them to be applied in various fields, from healthcare to finance. Continued research and advancements will further enhance their capabilities and reach.